morning, everyone. My name is Sabidur. I'm from UC Davis, third-year PhD student. It's a hard job to make an impression in a presentation after Professor Chan, but I think we can try.
We can do it.
Yeah. So I'll be talking about how we are using network data and machine learning to auto-scale the virtual network functions so that we can have better QoS and reduce cost. So this work was incubated during my summer intern at AT&T Labs. So I'll be going over why this problem is important and how it can save money. And then I'll be talking about what's the solution we are proposing and some interesting results and future directions. So to begin with, this idea of auto-scaling is very simple. So you deploy more resources when you have higher demands from the customer or in the network, or especially in the cloud computing when you have more workload. And you reduce some of the capacity, some of the resources, maybe take it to some other customers, shut it down, shut the VMs down when you have less demand, less workload. And in the earlier days, we couldn't do it in the network because all the network functions are running on top of hardware boxes. You cannot really auto-scale them. But in recent days, there is this change that the network functions like firewalls and net boxes are coming in on top of x86 servers running in VMs. So now we can do auto-scaling in network functions. But of course, the workload in cloud computing and the network is different, and also the way we collect data from network and cloud computing is different. So there needs to be new methods, and I'll show you how the older method we are improving the older ways of doing it. So, so going into why we want to do it, the biggest motivation is money. So the way the cloud computing models the pay-as-you-go model is that I just take resources, I pay for what I use. So the same thing can be done now that we have virtual network functions. So from the infrastructure owner's point of view, they will save some money using the resources for other customers, shutting down the VMs, operational costs. And also it will be a very new interesting feature, pay-as-you-go models for their customers. And from the customer's point of view, of course, they will be saving in terms of leasing costs, and also they will have more flexibility in management, and they don't have to worry about, okay, I need to manage my resources, my own. The auto-scaling algorithm will take care of it. So, so this actually takes to when we talk about 5G and beyond and edge computing, all the applications that are running on virtual machines, the computer network applications can be benefited from these auto-scaling methods that we are talking about. Going into the problem statement, so in the figure I'm trying to show the very high level what is happening. We look into the network status data, we pre-process the data so that we can use it into the auto-scaling method, and we also look into the, of course, QoS requirement, one of the important stuff that if I keep shutting down resources and violate QoS, that's going to impact my cost. And then once the decision is made, okay, I need 10 resources, I need 5 resources, then there is some actual mechanism which takes the decision which one to shut down, how to reroute the traffic. So in our study, we are assuming that the network manager will use some, let's say AT&T's eCom, some kind of management platform to do the actuator thing. So our focus is on auto-scaling algorithm and methods that can learn from the traffic data and make decisions. So for that, we need this historic traffic measurement that we talk about, and then the output would be for a given future period, how many resources are good enough for the QoS and the minimum that we can deploy. And the objective is, of course, to save money and improve QoS at the same time. So going back into the literature, just to give a very high-level idea what there has been happening in the cloud and both in the cloud computing area. So traditionally, this threshold-based approaches, and there are variations on that. it looks into the data points, works on some threshold, and for the first example, the decision is 8 VNFs are good enough for my current traffic. Then it goes down, goes up with the threshold. But as you can tell, in most of the time, the decisions that are made are, in many cases, they will be over provisioning and under provisioning resources which we actually don't want. And there have been improvement proposed, like prediction-based approaches, which actually looks into the other data points and tries to predict the future decision, like a time series analysis and things like that. And we actually compare our study with this prior study, which essentially does something similar, a little bit improved version of this. So what are we doing new? So we are essentially going back to how long-term memory of machine learning can help us to learn from the prior instances. So we go back to days, previous hours, and actually cut down the data and see how the previous auto-scaling decisions could be accurate and learn from that. And while learning that, we observed that there is actually these two ways of making decision. One way is QoS is my priority. So not for all the applications that QoS is a priority. For that, the customer can say, okay, this application, the QoS is not that important. So let's just go with the minimal resources that serves, and I'll work around the burst traffic. So we propose these two methods of doing it. One is Q is the priority QML, and cost is the priority CML. And from there, how do we work on the training data, and how does the machine learning learn from the data? So fortunately, we have a publicly available data that is used in this recent deep learning study. We use that. We take that data, break it down into auto-scaling decisions and multiple interesting features, and then we do the classification on top of that data, and then we train it over 20 days of data, 40 days of data. That's the max we could do, and then we look into how accurately that data is predicting the future virtual network decisions. So so our paper actually goes into all the features and all the details. So I'll go into the results to give you some idea how much accurate we are getting the results and how this can actually impact the QoS. So that will be the takeaway. So to start with, we see pretty much promising accuracy rate with 96% accuracy, and we also talk about false positive rates, another way of looking into the accuracy. And we compare it with this prior study, which does another proactive prediction method. And we also compare our results for multiple machine learning algorithms and observe that the random forest algorithm is performing the best with 96% precision and 1.1% false positive rate, which is a very good beginning point. So in terms of how we can save QoS and save leading cost in terms of that, we go into a SDN use case scenario, because recent surveys have showed that SD1 is one of the highest leading use cases for virtual network functions. So we look into a scenario with one HQ, which needs connectivity between 4 branch offices and needs the traffic to go through some virtual network functions. And we start with a scenario where there is no scaling algorithm being used for the network functions, which is the current case right now. And if we use the prior study MA, it suffers from some QoS penalties because of the wrong decisions it made. And we compared that with our studies, QML and CML. So the takeaway from this graph is that if QoS is your priority, you want to, your application is very QoS sensitive, then you have to go with the QML. Otherwise, if the application is not, if the customer feels like let go with some of the burst traffic, then you can go with the CML, which essentially, if the queue is not that significant, then CML is the better way to go with. And for the cost purposes, we look into virtual network function cost, network cost, and we take the values from estimation of that is provided from Google Cloud and Google Fiber. As you can see, the results show significant improvement. So to summarize and the future direction, the takeaway is that a lot we can do from looking into the data and from learning from it. And as we are talking about more and more flexible kind of network scenario, there will be more scopes to manage resources like this, including network resources and the compute resources in the network, in both edge and inside the network. And we also look into aside from the accuracy rate of our proposed method, we also look into different scenarios, like how the number of features are impacting the results, how the data size, if I train from 7 days, if I train from 20 days worth of data, how it improves. And we also talk about these virtualization technologies, like if I go with the virtual machine versus Docker containers, how does that impact? Because there are some characteristics that goes with that virtualization technology. I think these results are very interesting. I would strongly request that you go over the paper and look into the results. And as for the future works, this work actually has very interesting directions that this can go. The first one is so right now, as of our study is looking into how we can look into the data and use machine learning for better decision in terms of number of windows. But a lot goes in the back end, like which virtual machine do I shut down, and how do I read out the traffic load balancing. Those things, the action part can be a very interesting direction to look into. And another direction would be analyzing the operational and leasing cost for such use case, for more and more use case scenario like edge computing and 5G deployments. Another interesting direction would be, that is one of my favorite, is for this study we are looking into horizontal scaling. So every time I need new resources, I run another VM and serve the traffic. But another way of deploying resources is vertical scaling. So you have the same instance, but you add more cores and more memory to that VM, and that solution for that would be a lot different than how we did. So that will be an interesting practical way of doing it. And the last one is these virtual network functions are most of the time, many of the time, not most of the time, are deployed in service chains. So they're interconnected with some other virtual network functions, and it creates a chains of services. Let's say it goes through firewall, routing, then video optimizer, things like that. So in that kind of scenario, the auto-scaling gets a little bit more complicated and more interesting. So that will be another future direction to look into. So thank you for your attention, and I'd be more than happy to talk more about this.
Thank you.